In this video, we're going to talk about decibels and Bode plots, which are going to allow us to make much more elegant diagrams of what's going on in the frequency response of our system. So let's start with the transfer function of our generic low-pass filter, 1 over j omega RC plus 1. And I'll remind you that at small frequencies, specifically frequencies that are a lot smaller than 1 over RC, that transfer function is roughly equivalent to the constant 1. And at high frequencies, the transfer function is roughly equivalent to 1 over j omega RC. If I were to take that and plot it, you'd get this plot over here on the left. So at low frequencies I have a gain of 1, at high frequencies I have a gain that's asymptotically approaching 0, and this is a correct plot, but it's kind of a hard plot to read, and that's true for two reasons. One reason is that there's a lot of white space on here where there's really not much going on, so all the action is kind of crammed into one corner. The other problem is it's very hard to see shades of gray. So in other words, just by looking at the plot, it's very hard to tell the difference between a gain of, let's say, 0.1 and 0.01. And the reason it's hard to tell is, again, all that action is mushed down into a very small corner. And those shades of gray turn out to be pretty important in signal processing. So what we're going to do instead is we're going to rely on the decibel scale. So decibel scale is basically a log scale, as you've learned elsewhere. Decibels is defined as 20 log base 10 of the gain. So for example, if your gain is 1, that's equivalent to 0 decibels. The nice thing about decibels is that every time you increase your gain by 10, by a factor of 10, that makes your gain go up by a constant of 20 decibels. So a gain of 10x is 20 decibels, and a gain of 100x is 40 decibels, and so on. Equivalently, if you divide your gain by 10, so if your gain goes from 1 to 1/10, you go down by a constant of 20 decibels. Okay, so therefore a gain of 1/100th is minus 40 decibels. So another standard gain that you will probably see over and over again is the gain that we get at the cutoff frequency. Typically at the cutoff frequency we have a gain of 0.707, that's 1 over root 2. And if you take that and substitute it into the decibel equation, you get a gain of minus 3 decibels. And that's why you sometimes hear the cutoff frequency of a filter called the 3 dB point. So what I'm going to do now is I am going to attempt to plot our transfer function again, but instead of plotting it on a log-log axis as I did before, I'm going to do log of frequency on my x-axis, and I'm going to do decibels on my y-axis. And first of all, let me start by marking up my x-axis. So let's say this is 1 rads per second, 10 rads per second, 100 rads per second, 1,000, and I don't know, 10K, 100K. So that's what happens when you get a log plot. When you have a log plot, things that are a factor of 10 apart are evenly spaced. So at low frequencies, let's go back to our transfer function. We said at low frequencies we have a gain of 1, and as we've just discussed, a gain of 1 is equal to a constant of 0 decibels. So let's say that at low frequencies we have a gain of 1. Okay, and I'm going to dash that out for reasons that will become apparent in a moment. Now let's see what happens at high frequencies. At high frequencies I don't have a constant anymore. Instead I have a very different dynamic. What happens at high frequencies is that every time my omega is increased by a factor of 10x, so if I take omega and increase it by a factor of 10, the result is that my h is going to become 1/110th as big. Okay, so if omega goes up by 10x, h becomes 1 over 10 is 1/10th x, and that's equivalent to, as we've just discussed, minus 20 decibels. So in other words, at high frequencies, every time my frequency gets 10x bigger, my gain gets smaller by 20 decibels. So let's try that out and see what happens. So let's say my cutoff frequency is 100. Let me just go ahead and line that up a little better. Let's say my cutoff frequency is 100 rads per second. Essentially what you're telling me now is that every time I go up by a factor of 10, my gain is going to go down by a constant of 20 decibels. So let's say that that is 20 dB. Okay, and then every time, so if I was here, now I'm here. Let's try to draw that a little bit more cleanly. And then if my gain goes up again by a factor of 10, once again, if my frequency goes up by a factor of 10, again my gain goes down by 20 decibels. And effectively, once I connect the dots, I can see that what's happened is that effectively I've made this a line. So by going from a linear plot to a log plot, my high frequency performance now appears as a line. So that's minus 20, that's minus 40, and so on. And we can say that this line has a slope of minus 20 decibels per decade. All right? And the only caveat to all of this is that at the cutoff frequency, my gain isn't 0. My gain is actually minus 3 decibels. And that's why I drew the dotted line. So right at the cutoff frequency, it's actually going to dip down a little bit to minus 3 dB. Okay? Like such. All right, so that's your minus 3 dB point. Now, look how convenient this is. Suppose I came along and I wanted to know what is the gain at omega equals 2,000 rads per second. Well, one way I could do is I can go to the formula, I can go to the transfer function formula and plug in 2,000 and see what happens. But now the plot allows me a really elegant way of getting the answer yet another way. So here's how I would work that. I would say that I'm going to start at 0 dB and then I'm going to decrease at a slope of 20 decibels per decade. And how many decades am I going to go down for? Okay, so if I'm interested in 20, let me use a different color. So suppose I'm interested in 20 decibels, 2,000 rads per second. A lot to keep track of here. So what I need to know is how many decades it went down by. So this is the number of decades. So it's going to be 20 times the number of decades. So all I need to sort out now is how many decades are between 100 and 2,000. And the way I do that is just by taking the log of their ratio. So if I take log of 2,000 over 100, I get 1.3. Okay, and that tells me there are 1.3 decades between 100 and 2,000. If you're wondering what exactly that means, essentially what I'm telling you is that if I take my original starting value, 100 rads per second, and I multiply it by 10 to the number of decades, I get 2,000. That's what that means. Okay? So to go back to this, my gain at 2,000 should be my original 0 minus a slope of 20 dB per decade times 1.3 decades, and that's going to give me a gain of minus 26 dB. Okay, and if I want to know what a gain of negative 26 dB is, I can just work the gain equation backwards. So my gain will be equal to, if I go to my equation here, it should be decibels equals, where am I? I should be able to take decibels, so it's 10 raised to the negative 26 over 20. Okay, whatever that works out to, it should be a little bit less than 0.1. Okay, so that's the gain. That's a really elegant way of doing this, right? So using the decibel method, first of all, it gives us a nicer plot, and then it gives us a little bit easier way of analyzing and estimating what my gains are going to be at different frequencies.